Yo, 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 ladies and gentlemen, hackers and traders. My name is Dr. J, and welcome to the 7th in our series about building an algorithmic trading system. Today we're going to be talking about how we might use machine learning to build a better prediction of the future returns of cryptocurrencies, foreign exchange, equities, anything you like, anything where you're going to be trading in a high-frequency environment. We'll be covering why this is a good idea. We'll be looking at how to transform the data from our signals into a representation that can be machine learned. And then we'll be doing a bird's eye view of 3 machine learning techniques. That is linear regression, gradient boosted trees, and the good old neural network. It's going to be big. It's going to be fun. This is Hacking and Trading. Stay tuned. So remember, in episodes 5 and 6, we discussed how we would build signals that would try to predict future returns of assets using only the information we have available in our price books. We also came up with 2 concrete signals, the volume-weighted mid in episode 5 and the leader-lagger signal in episode 6. Now remember, any competent algorithmic trader would have 10 to 100 signals in their quiver, and each of those signals can be parameterized in ways that could mean multiply that by another 10x. So we're talking hundreds or thousands of signals. Now, any given one of those signals might be good at predicting the future, but we had a hunch that surely combining some of those signals would give us an even better prediction of the future. Now, obviously, we can't evaluate the performance of all those signals by hand. And moreover, we certainly can't predict what combination of those signals might work well together. I mean, the sheer combinatorics, they're exponential. So we're definitely not doing that by hand either. So we have to turn our hand to machine learning. But before we do that, let's have a look at the 2 signals we've already built and look at how or why they might do better together than they do on their own. So remember this chart? The top chart here shows the evolution of ETH-BUSD for a few seconds. And remember that these shaded areas here are the future returns of that ETH-BUSD here over a 200 millisecond horizon. So you can see where ETH-BUSD started going up there. Well, 200 milliseconds before that, the shaded region shows that in the future, ETH-BUSD is going to rise by 1 basis point. Similarly, down up here when Ethereum is going to drop, our shaded regions showing that drop 200 milliseconds earlier. So we're sort of transporting the future into the present, but we can do that because it's historical data. Obviously, we wouldn't be able to do that in real life. So most importantly, remember these returns here, these shaded areas, these are in basis points. Look at the y-axis here. It's basis points, 1 basis point, 2 basis point, 3 basis points. So in this case, an increase in price from 1198.4 to roughly 1198.5 over here, well, that's what this 1 basis point increase is in the future return. So in the second chart, the green line is the signal value for our volume-weighted mid signal. You can see it's quite a chatty little signal. It moves up and down all the time. It's hardly ever 0. And this bottom one, the purple line, is the signal value for our leader-lagger signal. Really a much simpler signal. It's much less noisy, and look how often it sits at 0. We've got a very chatty signal here, our volume-weighted mid signal, and we've got this leader-lagger signal occasionally gives some indication of the future, but most of the time it's just sitting quietly. You'll also notice that the green signal is much more chatty. It's a lot more loud than the purple signal. It has a range from, in this particular instance, -1 basis points all the way up to 3 basis points, whereas our leader-lagger signal hardly ever breaks an amplitude of plus to -1 there. So you can see this one's a much louder signal than that signal. And so we're going to have to also keep that in mind when we want to combine these things. We don't want one very noisy signal completely swamping out one of the other signals. So that's going to need to be taken care of by our machine learning as well. And then I guess most importantly, look how often our signals are agreeing with the future returns. Here, the future return is negative, and our signal is correctly a negative number. Over here, the future returns are positive, and our signals go positive. Same over here. Same over here. But also look at the occasions where the signal is getting it wrong. Here, the signal is saying it's going to move up, but in fact, the market ended up moving down. Or in this case here, the signal is still predicting a downward move, but the market's actually about to head up. Similarly, the purple line, it is in agreement quite often, but there are cases, here's one example, where the market shot up and the signal was wrong. But on the balance, it looks like this purple line is much better at predicting the future, but it doesn't predict quite as often as the green line. So we can see there are differences already in these two signals. One's very chatty, gets it wrong quite often. The other one's less chatty, but its predictions are kind of better. So really from these simple charts, we're starting to get the sense that it's kind of plausible that combining them may be better than treating each one on their own. How about when both of them are negative, that's when we're going to spit out our signal saying negative. Or how about when both are positive? When they're in agreement, maybe that's a way to combine them. We're going to have to think of quite a few ways to combine them. So for example, perhaps we only output a signal when our two input signals agree in direction. And then, well, how do we combine them? Maybe we take their average, or we add them together, or we take the maximum of the two. But most importantly, we only spit out a positive number when both of them are positive, or a negative number when both of them are negative. Perhaps another way we can combine them is just to add their values together. If they both agree in direction, well, then adding them together is going to make an even bigger sum in that direction, positive or negative. Whereas if one of them is positive, one's negative, when you add them together, it's going to tend to dampen their sum down towards zero. So you'll get a very low signal reading if our two underlying signals don't agree with each other. But perhaps there are even smarter ways. I mean, in this case, we're only looking at two signals for a very short period of time. We have no idea how they perform across a day, a week, a month. We're looking at literally 3 seconds here. And also, they're only two signals. So what's going to happen if we had 5 signals? Or what would happen if we had 100 signals or 1,000 signals? Obviously, just adding together 1,000 things is not going to give us a very good result. We're going to have to come up with something smarter. So let's zoom out from that 2 seconds and look at what these signals look like over a week of data. Remember these charts? The top 2 are our signals, and I've included a few at the bottom, a variety of other signals from my collection of signals. Recall in this style of chart, on the x-axis is our prediction of the future of the market, and the y-axis is the actual prediction. So what we're looking for is like a flat 45-degree pancake, where when we're predicting a big positive move, the market actually is a big positive move. When we're predicting a negative move, the market is actually a negative move. And in this top left corner and bottom right corner, well, that's where we've predicted the market's going to go down, but it actually went up, and vice versa. So we want very few points in these top left, bottom right quadrants, and we want most of the points to lie along this nice 45-degree line. If only we could find a signal that would lie perfectly on that line, but we sort of have to be content with a flattish 45-degree pancake. So let's have a look. There's several things that stand out from these charts. First of all, well, our 2 signals are actually pretty good. Most of the time they are in the correct quadrants here. Okay, this one does have a bit of noise here and a bit of noise here where it's incorrectly predicting the market. Whereas this one, man, it's pretty much always right, at least directionally. There's a few smatterings of when it's incorrect, but the bulk of the time it's getting the direction right. Secondly, you can very much see from this that one of the signals is much more chatty than the other. This signal over here has way more data points than the signal over here. And when it has data points, look how far out they go. They're very extreme numbers. Whereas this lead lagger signal tends to huddle around 1 or 2 basis points. It's not very chatty. It doesn't signal very often. So you can really see these are really different beasts at play here. We're going to want to combine them. So this is an interesting takeaway, that signals that are very chatty and signals where, well, we'd love to trade often on their predictions, well, they tend not to predict very well. And on the flip side, the signals that do predict very well, well, they hardly ever give a signal. So yeah, we may be able to predict the future very well, but if we're only going to be able to predict it once a day, well, we're kind of wasting our time. We want to be trading like several times a minute kind of thing. So it's no good getting it right once a day if you're only going to make a few basis points. You want to be getting it right thousands of times a day. So we got to find something in between these two, something that's very chatty, but also correct most of the time. So again, we like, oh, can we take the qualities, the chatty qualities of this one, but have the predictive correctness of this one? So off the top of my head, I can think of a very good example of where we might say, well, let's only listen to this signal if it doesn't disagree with that signal. If that signal's equal to 0, we're still going to use the signal's value. It's only when that one's saying it's going to be positive and this one says it's negative, we're going to skip that. Or when this one says it's going to be negative and this one says it's going to be positive, let's skip that. So you can see there's sort of an and kind of operation there. If this one and that one agree, then let's do that. Or at least if this one does not agree with that one, let's go with this one. So you can see there's already a way of combining them that might make more sense than this one just on its own. So the holy grail is, can we sift through hundreds or thousands of signals? Often they're just hunches that we had about how the market might work. They may be really bad at predicting the future. We don't know. We don't want to evaluate each one very carefully. So can we sift through them all and somehow in a very automated way combine them to produce one signal that not only signals often, but B, signals correctly most of the time? So our inputs to this process are going to be thousands of mediocre signals, and we're going to spit out a single very good signal. How are we going to do that? So the first thing we're going to need to do is sample our historical data and come up with a selection of samples that over time show the actual return of the market. In this case, it's going to be the yellow row. And then the value of each of our signals at that point in time. So we're going to end up with these columns of what the market actually did in its future and what each of our signals spat out. And then we're going to move on to the next one and map those down to their values there. Move on to the next one, map them down to their values there. Once we have these rows and rows and rows of data, we're going to then be able to do some serious number crunching. But the problem is, how much data do we need? Obviously, 3 seconds of data wouldn't be enough. In my case, I tend to aim for like 10 days worth of historical data. If you go back too far, the data sort of becomes irrelevant to the present. If you don't go back far enough, well, A, you don't have enough data to do real machine learning, but B, you might also just be overfitting to an event that happened yesterday, but it's not really representative of the whole week. And you wouldn't want to use that event from yesterday to predict the future. You'd rather have a week or two's representative data when you're starting to predict the future. So a sweet spot between having too little recent data and too much old data is maybe sample more from like the less recent past. So maybe more samples from yesterday and the day before, and then have a few samples from way back in time, like 10 days ago, 2 weeks ago. That way you're sort of getting the power of the data really represents the last week, but you're also getting some information from 2 weeks ago in that data set, so you're not overfitting too much to recent events. Another thing you have to think about is that signals are often zero, and even the market returns are often zero. Sometimes the price can just sit still for a few seconds, a few minutes. You're not going to get much information out of that market if you have too many zeros in your data set. Too many zeros will really mess up the machine learning because there's not much information there if most of the time the signals and the outputs are zero. It's like, we'll just throw them all in. So you need a balance between how many times you're going to include zeros and how many times you're going to actually include signals where they're large deviations from zero, where they're predicting the future. But remember, if you include too few zero returns and signals, well, then the machine learning is not going to penalize those signals that are very chatty when actually the markets are quiet. So you really do need to strike that balance. So there are a huge number of these balancing acts, and in some future video we'll certainly come back and dig deeper into how, or various strategies to mitigate what are the pros and cons of this balancing. But no matter how we end up doing the sampling, what we're going to end up with are rows and rows of data, where the first row here is the actual future return, and all the other numbers in that column are the actual signal values at that particular point in time. Now we want to crunch this data. So here you can see how I've just compacted them up, written them more neatly in a more compact matrix format. Along the columns, we have the N observations, where we sampled points in the past. And in the rows, we have a future return and the value of each of our signals. Let's say they're M signals. So we have an m by n matrix of numbers here. So the number of columns n here can be in the hundreds of thousands or millions of columns. And that's going to depend how you sample over 1 week or 1 day or 1 month. And then the number of rows, m, is going to be how many signals you've come up with. So we're talking hundreds, maybe thousands. But actually, to conform with the convention of most mathematics textbooks, when we get later to the machine learning part, it makes sense to actually transform the matrix so that we have millions of rows. The observations are now the rows, and the columns, the m columns, are your signal values. And we separate out the future returns. So you can see we're sort of ending up with this n by m matrix here, which is our signal outputs over time. And this yellow n by 1 column vector is the future returns over time. And actually, this representation is not just useful for the mathematics, but it also makes an amazing difference to the performance of your regression or your machine learning on most modern day architecture. By storing the data row order first, you behave much better in the CPU caches, so you can speed up your computations by, I don't know, 10 to 100x. So remember to keep it in this format if you're building the regressions yourself. So given this matrix representation, our job simply boils down to, given any observation I, how do we combine these m signal values in this row? How do we combine those m values to produce that single r value? And that we have to do that for every single row in these huge matrices. But the job is take these m values at any given observation point I and predict the return at that time I. So I like 3 ways of solving this problem. I've tried hundreds of methods, but there are 3 that have risen to the top, mostly because they're easy to understand, it's easy to interpret the data they're spitting out, and they're quite diverse in the way they work. So they each have their pros and cons. Diving into those pros and cons will require a future video for each of them. So remember, get your friends to subscribe so we get to those future videos. So let's do a high-level overview of each one. First off, we have good old trusty multiple linear regression. In a nutshell, we're trying to find a linear combination of our input signals to produce our future returns. That means we can scale these numbers however we want, each of our signals. We can multiply them by a big number or a very small number, and then we can add together or subtract those signals. And it's a very simple piece of maths. Do some multiplications and then add the individual signals together, and that gives us the answer for our future predicted return. Generally, what you find from linear regression is signals that are very good at predicting the future returns tend to get a big multiplication amplifying number, and signals that are really bad at predicting the future get a very small amplification number. And so when you then add them together, the good ones are more weighty in that sum than the bad ones. And then you sort of divide through to get a normalized number for the returns, because obviously adding a whole lot of things together, you're going to get a very big number of that addition. So you sort of divide through by some normalization term to come up with the final resulting prediction. So this machine works really simply. Because we sort of adding together things that should agree when they're predicting the future, well, if we add them together and they're all of the same sign, well, then that addition is going to tend to amplify the combined contribution to the sum. But if some of our signals disagree with each other, well, then when you add them together, they're going to sort of dampen down towards 0 and not predict any future or predict a 0 future return. Now, linear regression comes with a huge statistical background, a lot of requirements and assumptions about the underlying data. Things like there should exist at least a linear relationship between the signals that are going in and the returns that are coming out.
The data should at least be normally distributed.
The data must be multivariate normal. The data must not be collinear. The data must be stationary. The data must be homoscedastic. The data must be blah, 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 blah.
So let's just say, if we close our eyes tightly and ignore all the elephants in the room, multiple linear regression is actually a really good starting point for selecting signals, combining them, and coming up with a much better predictive signal. And just remember to use something called the elastic net regularization with cross-validation, and that'll make most of the scary elephants disappear. The next machine learning tool in our toolbox are gradient boosted trees, or more specifically, extreme gradient boosting, or XGBoost. Rather than using maths to add together the outcome or the value of each of our signals, boosted trees basically ask questions about our signals. And after it's asked enough questions about those signals, yes, no questions, it simply gives the average return that is experienced by all the samples that fall into that state of the world. So we ask a whole lot of questions, and then for all the samples that land in the true part of those questions, we take just the average return of that segment. So for example, in this toy example over here, say you know the age, gender, and occupation of a whole group of people, and you want to answer the question, does this person like computer games? Or how much does this person like computer games? Give it a positive number if they really like computer games, or a negative number if they don't like computer games. Well, an obvious thing might be to do like, well, are they less than 15 years old? If they're less than 15 years old, yes. Are they male? If the answer is yes, well, most males under the age of 15 years old like computer games. On average, we give them a +2. Another route down this tree might be, are they less than 15-year-olds? Yes. Are they male? No. Okay. Well, some girls love playing computer games, but it's a far smaller number than guys that play computer games, so we only give a slightly positive number there. But if already we asked, are they less than 15 years old, and you're like, no, they're older than 15, it's like, well, that's everybody else. They probably don't like computer games. Give them the score of -1. So you can see in this toy example, you're getting a sense that you might actually be able to predict quite well whether someone likes computer games just based on their age and on their gender. So in the case of our signals, instead of asking about age and gender, we might be asking, is the value of signal 1 greater than 3? And if so, is the value of signal 4 greater than 5? And if both of those signals are really shouting loudly, well, we found in the market returns of our historical market data that in that particular case, the market always goes up 4 on average. Well, there we found a state of the world. And so it's the job of XGBoost, or these boosted trees, to work out the correct questions to ask to end up in various states of the world that we can then just state, well, on average, in this state of the world, this was the future return. And it makes sense. If you say, if signal 1's less than 0, and signal 5's less than 0, and signal 10's less than 0, and signal 14's less than 0, well then the returns are probably going to be less than 0. But you can see it can get smart in like, well, if signal 1's less than 0, but signal 2 is greater than 0, and signal 8 is greater than 0, well, now we're starting to enter this weird world of if this, and this, and this, and this, and it gets really complicated really quickly, but that's not our problem. That's the problem for the machine. So in this example, these are very toy trees. Like this tree is only asking 2 questions. Imagine in the real world, you're asking, these trees are 7 or 8 levels deep. So you're asking 7 questions one after the other. So these trees become really deep, they become really wide. And the end cases here, in this case, we just have 3 cases here. But in the real world end cases, you could end up with hundreds of world scenarios where you've asked these questions, you end up in a certain picture of the world, and you just give the average answer for that world scenario. So you literally can have hundreds of these end states. So it may sound very simple, but I mean, this is an unbelievable technological achievement. XGBoost, the speed at which it is able to work out what questions to ask, how many levels deep to ask it, and then come up with these end world states where the average that you have in that area has a very low variance, very low standard deviation. If you ask these 7 questions, 99% of the time, this is how the market responded. This technology wins machine learning competitions that bespoke, like machine learning, like tailor-made machine learning techniques fail to achieve very high results. This really simple generic technique is just incredible. I mean, it's one of my favorite toys. And then, I mean, just to give some depth to what we're actually doing here is you don't actually just build one tree. You build the first tree that then you compare how well it's predicting the future with the actual future and look at the errors that makes. And then you make a second tree that tries to predict what errors the first tree is going to make. And then you make an even better prediction by making the prediction and then fixing the errors that you predicted. And then you do that a third time and a fourth time, sometimes up to 10 times. These things are incredibly powerful, but most amazing is the dynamic programming that is used to work out, well, what are the best questions to ask if you're only going to ask 7 questions. Really incredible stuff. Love XGBoost. And the final machine learning technique we'll be covering today is the good old backpropagation neural network. I fondly remember learning the mathematics of this guy back in 1999. Back then, it was a toy machine that could solve toy problems. It was just like something of mathematical interest. But it was still amazing that such simple math, such a simple idea, could solve those simple problems. I mean, these problems were simple things like recognize the digits from 0 to 9, or classify groups of people into height or something like that. Like really simple problems. But today, with our incredible new hardware, these machines scale up to matrices of billions or even trillions of numbers, and these things can produce beautiful art, answer any questions you have about the health of your cat, and probably even put us out of work in the near future. But while I won't dive into the details today of how backpropagation works, all I can say is that they have similar kinds of power to multiple linear regression. But they do have a few extra bells and whistles, notably something called the activation function, which allows them to learn some non-linearities in your data, whereas linear regression can only find linear mappings between your signals and the future returns. Neural nets are able to attenuate those guesses, like include non-linear features there. So neural nets are slightly more powerful than plain linear regression. But they're certainly much slower to train, and they have thousands of knobs and dials that you're going to have to play with to find the neural net that works best for your setup, for your particular learning needs. But nevertheless, remember to love this little neural net, because one day it will be feeding you. Right, so where have we ended up? We've covered 3 machine learning techniques that can take historical data, look at the signal values that we would have come up with on that historical data, and map those signal values to the historical future returns. And so our big assumption in this is that if we're able to tell the future in the past, well then surely that same little machine can tell the future in the present. Surely the markets have not changed so much from last week to this week so that our little predictor that worked so well last week in historical data won't work well this week. Surely indeed. But remember, this thing can only predict as well into the future as it learned to predict in the past. And if the past is significantly different to what's going on at the moment, those predictions are going to be awful. So fitting these things or making these machines learn is not a one-off task. You have to continue to be fitting these things regularly, like maybe once a week, once a day, once an hour. You got to choose the camera of how often you're going to be doing that. But remember, this is all automated, so you don't have to be doing this by hand. There are thousands of instruments out there. Each instrument requires its own predictor of the future. There's no way you could be running this by hand. It has to be automated. But remember, if there's a huge event like, I don't know, the bankruptcy of FTX, or the Fed suddenly tightens interest rates crazily, the markets tomorrow are going to be nothing like the markets were last week. And so you're sort of left in a bind. You don't have much data to train on because you've only got like the last hour or two since the Fed tightened rates, and you want to be predicting the future. So if you use too little data, well, you don't have much data to fit with, so your predictions of the future are not going to be great. It's probably going to overfit to something. But if you use too much of that historical data, you're going to be including market events that have nothing to do with how the market's going to behave going forward. So there's constantly this tension between how far back you want to go, so how much data you have, and how much recent data you have. That tension is ever present, but it's the best we can do. And luckily, all your competition has the same problem. So grin and bear. So hackers and traders, I hope you enjoyed this episode. It was obviously a very high-level examination of how machine learning can be used in high-frequency trading. We'll need to dedicate an entire video to each of those machine learning techniques. And so, guys and girls, please help us get there. I'm only going to do those videos if I think there are enough people actively learning from it. So get anyone you know who might be interested in this to please know about the channel And most importantly, subscribe to it so that I know that there are actually people out there who care. And so if you haven't subscribed already, do so right now. Hit the subscribe button, hit the alert button, and also give this video a thumbs up. That's the only way we're really going to grow this channel together. And so, fellow hackers and traders, this is Dr. J, signing out. See you next time. Ciao.